Hey guys, welcome back. This is our second day of Chapter 9 for re-expressing data. We're going to be looking at measuring captured alligators for our example for today. So kind of have a cool graphic for you here. But before that, let's revisit the goals of re-expressing data. So our first one is to make distributions more symmetric. So here we looked at like the Fortune 500 companies, which are the 500 largest companies in the US. And here we're looking at the assets, which are measured in hundreds of thousands of dollars. This is like how much the company owns, like all of their property and the value of the company, like the whole net worth of the company all put together. So this value here would actually be close to 4 billion if you add all the zeros together. So there are only looks like two companies that are worth over $4 billion. Then there are several that are worth anywhere from 2 to 4 billion, but most of them are worth less than 1 billion or around $1 billion. So notice that this is very clearly skewed to the right. This distribution of this data here is going to be skewed to the right. And anytime we have data skewed heavily to the right, we can use the logarithm, re-express the data by taking the log of the assets, in this case, in order to make the distribution much more symmetric. Now the reason that this works is a logarithm is dealing with exponents. So as it grows here, like 10 to the first power, that's just going to be 10, right? Log of 2 would be 10, a base of 10, which is the second power, which would be 100. Log of 3 would be 1,000, and then 10,000, 100,000, and then 1 million. So just going from 1 to 2 to 3 to 4 to 5 to 6 is increasing by a magnitude, a scale of 10, right? For each one, just adding another 0. So it takes these values that are really far out, and it's just basically saying how many zeros do we have there. So a value of 4 would say there's 4 more additional zeros beyond whatever each one of our units was in 100,000. Okay, so our 4 billion would be about right here. 2 billion would be, if I'm doing it right, I'm not sure exactly, but anyway, in general, you can see how logarithms are dealing with exponents. And so what's amazing is that all the data that's so far out is brought in close here, and all the data that was really close and crowded together at the beginning is going to have much more spread, much more variation, kind of spreading that part out. And it's really cool because it makes it much more symmetrical in this case. And in fact, it really even looks like a bell curve, right? Unimodal and symmetric. That was terrible. Let's try that again. Much better. It's been a while since I made a video, so I haven't had to have my handwriting skills. They're struggling here. Anyway, so it looks like a normal model, which means we can use a bell curve. We can use a model to represent this with, and then we can use z-scores to compare different companies together and stuff like that. So anyway, it's nice. Another thing is that the logarithm re-expression and the natural log re-expression, they do the exact same thing. They have the same effect on it. It will change your numbers on the bottom because natural log has a base of e, which is like 2.8 something, where the logarithm is a base of 10, like what we see over here. Then it makes the distributions more comparable as well. So if we broke down each one of those Fortune 500 companies into whatever their market sector was, like energy, finance, high-tech, manufacturing, medical, retail, transportation, and other, it's kind of hard to compare these distributions together because they're all skewed, just like the original data was heavily skewed to the right. So when we take the logarithm of the assets, then all of a sudden, all the stuff on the bottom kind of gets spread out. The outliers and the far skewed stuff on the top gets brought in closer, which is what logarithms do, and now it's easier to compare. You can tell much more easily comparing what's going on between medical and retail, etc. You can tell which one has the largest spread with technology, which one's the most consistent, like retail or transportation as well. Also makes scatter plots more nearly linear. So here we have the fuel efficiency and the weight. This is the one that we re-expressed with the reciprocal by changing the fuel economy from miles per gallon to gallons per 100 miles. So the amount of gallons that it takes for you to go 100 miles or whatever. So when we took the reciprocal of that, it re-expressed it, made it much more linear, which is nice because then we can actually use a linear model instead of having to use a curved model, which we don't get into in this course. It also makes the spread much more even. So here, notice that all of this is skewed to the right. If I drew a histogram of this, like if I collapse this and where I wasn't looking at the sales at all I was looking at was the assets, so I collapsed it to one variable, it would look skewed like this. So we would have like a histogram. Handwriting is really rough. That'll look something along the lines of this, and we have very few that are over here as well, right? So it would be skewed, heavily skewed towards the larger values, which would be skewed to the right. So whenever we take the logarithm of the assets, all of a sudden all this data that was crunched up together towards the bottom, the low end, that gets spread out because of just the properties of exponents with logarithms, and then all the outliers that were really far out by themselves that were skewed, they get brought in closer, and so those are just these values on the top here. So it's really nice, makes the spread more even. And then again, doing the logarithm of sales and logarithm assets, that's actually the power model. We'll talk about that tomorrow. It's really, really powerful, and it can take really messed up skewed data for both sales and assets and make it linear so that we can use a linear model for it. All right, so we are going to talk about the ladder of powers. So ladder of powers is the kind of a hierarchy of re-expressions of powers of re-expressions. Okay, so think of it like a ladder here. The power, the exponent to the first power is going to be the actual raw data itself. So here we have the length and the strength. We're talking about monofilament fishing line. So they sell them all about the same size package. You can buy them that have a higher test strength, or excuse me, a breaking strength, which is basically what they're tested or rated to break at. So larger fish, if you're fishing for larger fish, you got to have a higher test strength for your line. But the problem is whenever they make the line stronger, thicker, right, then it's not going to, you're not going to have as long of a line in that package, because they're all selling the packages for about the same weight. So the longer the length of the line, the smaller the strength is going to be. So if we increase the strength of the line, the test strength, then the length of the line is going to be much shorter. Okay, so essentially that's going on. It looks like there's a reciprocal relationship going on with that as well. So just right off the bat, if I see something that looks like this, I mean, honestly, it looks like y is equal to 1 over x, which whenever we graph that out, looks something along the lines of that. It's a reciprocal relationship. So what I would want to do is do the reciprocal of the y value, the reciprocal of the length, so 1 over yards or whatever, and take all those values and take the reciprocal of them, which is the -1 power, and that would be the one that I would look for, probably this green one down here. So starting at the raw data, the power of 1, I don't want to square it. That'll actually make it worse. I can take the square root, but it's not going to be as good. Then the logarithm is a 0 step, which it just is. Just get over that. Then the reciprocal square root, which is the opposite reciprocal square root, which is -1/2 power, and then the opposite reciprocal is going to be the one that we were going to be looking for. Okay, so let's see what these look like whenever we do this. So the next one we could do is going to be the square root. Well, if I take the square root, you'll notice it's improved, like it's closer to a line, but it's not quite a line. I can actually graph my line here if you want to see kind of for reference. Oh, that's nice. All right, so then the next one after that would be the logarithm. So we're moving further on down our ladder of powers until we find the one that's appropriate, the one that looks right. See if I can fix that. Okay, cool. So it's even better. The logarithm is getting better. So we're just going to keep going down the ladder of powers, the opposite reciprocal square roots, which is even better, but not quite straight, still has curvature to it. So then the opposite reciprocal, which is the one that we're really looking for, which is going to be right there, which is lovely. In fact, that one works out really, really well. We could go even beyond that if we wanted to, but there's really no reason to. We could do the -2 power if we wanted to, but then it's going to probably start curving back up towards the top. So we found our appropriate one. It even made sense kind of mentally with the original one, so I'll kind of move these out of the way. And you can see this one looks like a reciprocal. Sure enough, it was a reciprocal. So what we're saying is that there's a reciprocal relationship between the length and the strength. So as we increase the strength, we increase the thickness, which means that you have less that fit on that one spool or whatever in general. Okay, cool, kind of cool. So ladder of powers, we can also move up by squaring the data. We square the data if it looks like the square root curve and it's kind of curving down. So then squaring it or cubing it would straighten it out. All right, so when do we square the data? Well, we square it whenever the data is kind of curving down like this. Also when the data is skewed to the left. And if you think about it, when we square it, things that are smaller are going to not be as affected, but the things that are bigger are going to be pushed out even further. So 2 squared would be 4. 4 squared would be 16, right? 6 squared is going to be 36. 8 squared is going to take it all the way up to, I'll just leave that. It's going to be, 64, and then 10 squared is going to go all the way up here to 100. So it's going to take these values that are higher, and it's going to push them out, and it's going to kind of make this more symmetrical, which is nice. And the things that are lower are not as affected by squaring the data. Okay, so anytime we have data that is, this is also, if we collapse this, you would see that most of the data is on the top here, and then it starts spreading out as we go here. So it is, again, skewed towards the lower values, just like this is skewed towards the lower values. Anyway, kind of hard to interpret. All right, looking at the dive heart rate of the penguins, so the number of dives that they're able to do with the dive duration or whatever. Anyway, this one is skewed to the right. This is an example from the book if you're curious about it. So it is skewed to the right. Whenever we do that, we're gonna take the square root of the data or start moving down the ladder instead of moving up the ladder. And what that's gonna do, the square root is gonna take things that are towards the bottom and it's gonna give them, it's going to spread them out, okay? And then things towards the high end, they're going to be brought in even closer. So all this stuff that's all crunched up is going to get spread out, and then the stuff that's further out is going to be brought in close. So similar to a logarithm re-expression, except square root's not as drastic as the logarithm. If we go back to our ladder of powers, you'll notice that the square root is right here where the logarithm is a 0. And if it gets even more drastic after that, then we start going into negative powers, which are going to be reciprocals, like reciprocal square root or the opposite reciprocal. All right, so logarithm re-expressions are when we use that when data grows by percentages like populations or salaries. So heavily skewed data here, we use log of assets when it's heavily skewed to the right. All right, the negative reciprocal square root. So the negative part preserves the direction. So if I just take the reciprocal square root, what ends up happening here, just like on the reciprocal here, is that instead of having a negative association, now it becomes positive. So what we do is we actually do the negative or the opposite reciprocal square root, which is going to preserve it so that it's still a negative association. So that's all the negative is doing there. Anyway, so we preserve the direction when we're taking the square root. Then next, the lowest one that we have on our ladder of powers is the negative reciprocal. But we try this when we have two ratios of different quantities, like miles per gallon. Then we switched it to gallons per 100 miles or whatever. Same thing with miles per hour or hours per mile. Anytime you're dealing with ratios of quantities, and if you accidentally do one of them backwards, you'll get kind of a reciprocal association instead of a linear one, which is what we really want. So we can use a linear model. All right, so here's our ladder of powers for the dive duration. This one is going to be skewed to the right, so we want to go down our ladder like closer to the 0 step. If we take the square root of the data, I kind of skipped that one, but if we go to the logarithm of the data, you can see what happens. And I took this from the book, so we have some nice graphics here. So instead of being curved down, it's now curved up, kind of bowed up. And then here, instead of being skewed to the right, it's more symmetrical, which is nice. What happens if we go even further on down the ladder? Well, if we go further on down the ladder, it's actually going to, at some point, it's going to be too far. And now it's curving up instead of curving down, and it's skewed to the left instead of being skewed to the right. So there is kind of a Goldilocks, or one that's just kind of right. The logarithm actually seemed to do a pretty dang good job. So I would stick with the logarithm on this one for the dive heart rates. All right, identify the explanatory. So we're doing the alligator one. So scientists wanted to be able to estimate the weight of an alligator based on the length of the alligator from a photo of a trail cam or something like that. So they captured 25 alligators and they wrapped their mouths in duct tape or whatever, just made them safe. Did some Florida redneck stuff, and then they measured the lengths of the alligators and they measured their weights. So we want to identify the explanatory variable and the response variable. So are we using the length to explain the weights of the alligators, or are we using the weights to explain the lengths? Well, naturally it kind of fits that the length would be our explanatory variable and our response variable that we're measuring is the weights of the alligators. Sketch a scatter plot. So we're going to put that in the calculator. So if you go to stat, edit, you have it on your homework, the data itself. So in list 1, that's going to be our explanatory list, which will be length, and list 2 will do the weights. So that's all we need for that. And then to visualize that, the first thing we want to do, because it's kind of hard just to read the raw data, is we want to create a scatter plot. So go to second, y equals the stat plot. We're going to do list 1 to list 2. So second 1, second 2. Okay, cool. And then zoom 9 to do zoom stat. Okay, so I've got a model that's being graphed out here and I don't want it, so I'm going to turn it off. Okay, there it is. So we notice that our data itself is actually going to be curved. It's exponential. It looks kind of like y is equal to x squared, or maybe even x cubed, because we don't know if it goes negative here. But anyway, what do you see? Is it linear? No, it's not a linear. It's not a correlation, so it's just a curved association. It's strong, it's positive, and that's pretty much it. All right, create a linear model for the data. Well, if we do create a linear model for the data, I guess I can show that. I don't know if I actually had it here. No, yeah. So if I end up creating a linear model for this data, it's not going to fit it very well. It's clearly, we're fitting a round peg in a square hole or whatever. So the way that we would do that is going to stat and then arrow to the right to calculate. We're going to do the fourth option for linear regression, and then we'll do second one for our x list. Our y list is going to be list 2. We're going to store the regression equation, go to variables, y variables function. We'll store it as y1, then hit calculate. Okay, so that's all this stuff here, same thing I've got there. And then we want to, if we hit graph again, it'll actually show us the line here, which is kind of what I'm showing there. And then from here we have our A and our B. I guess I'll quit out of this. If you ever want to go back to the actual data from the linear regression, you just arrow up and hit enter again, and I'll give it back to you. So our A is going to be our slope, and our B is going to be our y-intercept, so that's going to be our equation. Write the linear model for the data. That's basically just wanting to know the linear regression line or the line of best fit, and always write it in context. So instead of using y and x, do like predicted weight with the hat. So weight hat is equal to the slope times the length minus the y-intercept, and that's going to be the line given here for the model. And then we want to graph the residual plot to check to see if it's appropriate. Clearly we know it's not going to be appropriate, but residual plots are helpful for that. So go to second y equals, and now instead of graphing the x list of list 1 across list 2, the response variable, the weights, now we're going to do it over the residuals. So it's still list 1 and then list 2. We go to second stat, which is a list option, go to the very bottom, that'll be your residual list. And then you can hit zoom 9 again. And I've got the model turned on automatically. I'm going to turn it off. Okay, so it is clearly curved, right? We can tell there's a pattern here. We're dealing with, we don't have any data in the bottom and top here, so clearly it's curved. We're trying to fit a linear model with curved data. So we need to re-express it, just like we learned yesterday. So discuss the accuracy of the model, discuss the correlation, the coefficient of determination, scatter plot, and the residual plot. All right, so the correlation shows that it is strong and positive, even though it's not an appropriate measurement of the strength of the association, because it only measures the strength of a linear association. Since it's curved, we know it's actually stronger than that. But at the very least, it is strong and it's positive, pretty close to 1. The coefficient of determination tells us that roughly 84% of the variation in the weights of the alligators can be accounted for by the lengths of the alligator. The other 16% of the variation cannot be accounted for by just their lengths. Maybe that's because these alligators have a thyroid condition or something, so it's genetics. Their weight, it's not their fault, right? It's kind of fun. Scatter plot, we said that it was curved, positive. Residual plot clearly shows that there is a pattern, a curved pattern, so it's not appropriate. We need to re-express the data. The average error, or the standard error, not standard error, sorry, it is the standard deviation of the error, standard deviation of the residuals for the model is going to be 52.87. The way I found that, you can take the residuals, I guess I'll show it to you real quick. So if you take the residuals themselves and try to run a one variable statistics on that, so for list, I'm going to do second residuals, and if you do that, it gives you an error because it's reserved or something. So if you save the residuals as like list 6 or something like that, then you can run it, then you can get a standard deviation. So that's how I do it. I had to get creative on some of the other stuff, but anyway, so this tells us on average our model was off by 57. So it's kind of like a margin of error. It's not quite a margin of error, which we'll get into later, but the standard deviation for the residuals is going to be 52.87. Okay, so this tells us, that allows us to assess the accuracy of the model, not necessarily how much variation we can be removed. They are related to each other, but this tells us the accuracy of the model itself. All right, so what about the nature of the measurements of the data that led us to need to re-express it? Well, if we're dealing with the length of the alligator, that's a one-dimensional length, okay? So that's a one-dimensional measurement. The area would be 2D, and then the volume is 3D. Which one of these is tied to the weight of the alligator. Well, assuming all the alligators have the same density, that they don't have a thicker skull than others or something like that, would mean that we would actually be tied to the volume, right? So as the length increases, the volume increases by a factor of 3, right? So we would actually need to take our weights and either cube our lengths. So take our lengths, which would be our explanatory variable. We either need to cube that, so take those to the third power, or take the cube root of the weights. Now we prefer to re-express the y variables instead of the x variables because it makes our models a little bit easier to interpret. So we're not going to do anything with the explanatory. Instead we're going to take the cube root of the weights, and then we're going to reevaluate it. So let's do that real quick. So go to stat and then edit. For list 3, I've already done mine, so I'm going to clear it out. So if you arrow up to the actual list itself, hit enter where you're like defining it, and then I'm going to hit the clear button and then hit enter. And so now I just cleared out list 3. So I'm going to go, yours is probably already cleared. So go to list 3, and I'm going to define it as the cube root of list 2. So hit second, list 2, and then I'm going to do the caret button to do the power of, and then I'm going to hit alpha x, and that'll do a fraction. I'm going to do 1 over 3, and that's going to be the cube root, which is like the 1/3 power. Then hit enter, and that'll define all these. So the cube root of 83 is apparently 4.3621 or something like that. So now I'm going to graph another scatter plot going from list 1 to list 3. So modify your scatter plot here from list 1 to list 3. Okay, and then hit zoom 9, and you'll notice, wow, it's straightened out. It's a lot more straight, a lot straighter than the original one that we had. All right, so find the actual run a linear regression for it. It's not a big deal. So stat, calculate linear regression. Our x list is going to be list 1 still because we didn't re-express that one. List 3 is our cube root of that. I'm going to store the regression equation as y2 this time. So that's going to be variables, y variables function 2, option 2. Okay, cool. So now it's gone up, our correlation went up, and of course it would because now it is more linear. So this is now the measurement of an appropriate measurement of the strength of the association. So it really was about 9.8 or 0.98 instead of 0.91 or whatever. We can now explain 96% of the variation in the weights by using the length. That's what our coefficient of determination means. So there's only 4% that's left unaccounted for by thyroid conditions. Our A and our B is definitely going to be different in this case. And then also notice a difference in whenever I'm reporting the model, I have to tell you we're doing the cube root of the predicted weights is equal to our slope times our length plus our y-intercept, or minus our y-intercept in this case here. All right, so that's our stronger model. Good to go. Sketch scatter plot, we already did that. So it is linear now. And so whenever we graph the residual plot, we notice that it's actually still got some curvature to it, even though it looks really, really linear. Now, keep in mind, the residual plot's always going to kind of like zoom in on what's going on here. So it does kind of still show us there is a bit of curvature going on because these values are kind of low, those are kind of high, and that's high over there. So we could go even further down a ladder of powers. Instead of the cube root, we could do the 1/4 power, or jump straight to the logarithm and take the logarithm of the weights, and that actually might do a really good job. So if you're curious of how it does, I think I've actually got that towards the end. In fact, I could jump to it real quick. So here's our original raw data and its scatter plot. If we take the square root instead of the cube root, it gets better, but it's not enough. Cube root is the one that we just did here. It made it pretty linear, but there was still some curvature left in it. So instead we go to the logarithm, and then notice now it's kind of curving up instead of curving down. But let me move this one out of the way so it's not quite so busy here. If we look at if we look at the plot of the residuals, notice that there's not a pattern anymore. It's not going down and up. It's just kind of a random spread. So the logarithm re-expression of y would actually be the proper one. That's the best one. Now, the one that made the most sense, given what we were doing with the data, going from one dimension length to 3-dimension weight, would be to do the cube root. So we would probably go with the logarithm be the best. If we go any further beyond that, notice now it starts to curve up. And the reciprocal square root and the reciprocal on the opposite reciprocal, then it's way worse, right? So that's kind of how the ladder of power does. In fact, I'll put them all up there so you can read and see all the things that go on here. Okay, so it gets better. Yeah, so it gets better and then better and better, and then the best one was green, and then the pink was worse, and then that one was there. So as we go down our ladder of power, you can see which one actually does it. What's actually fun is that statistical packages, oh my goodness, that is a mess over on the other side. Anyway, I could line it up, but ain't nobody got time for that. I got to keep going. So statistical packages, if you put all the raw data in there, you actually have like a slider that you can slide up and down. You can see it change those in real time and pick the one that makes the most sense and actually that re-expresses the data the way that we would want it to be re-expressed. All right, so let me go back. We'll finish those. So we already sketched that. We're good to go. Explain why your new model is better. So the new model is better because whenever we look at the residual plot, there's no more pattern. That's the first thing. Okay. Also, it's simple and it makes sense. We'll get into that tomorrow, but with the power model. Also, we can tell that it's better because our correlation, the strength of correlation went up. We can account for more variation now with our model. And so yes, it is a better model. And notice it is the cube root of the weight instead of just the weight itself. Use your model to predict the weight of an alligator weighing 90 inches. So what I want to do for that, the model was already saved as Y2 here. In fact, if I hit graph, it'll show us all that good stuff. So to evaluate Y2, what I want to do is go to variables, Y variables function Y2, and then open parentheses and evaluate it at 90. That'll be our X value. Now the problem with that is that this is not the weight of the alligator, that's the cube root of the weight of the alligator. So to get the actual weight of the alligator back, we have to undo the cube root by cubing this value. So do it to the power of 3, which will give you an approximate weight of, an estimated weight of 103.64. So if the actual weight of an alligator that was 90 inches long was 102 pounds, find the residual. So the residual is the actual minus the predicted. So 102 is the actual minus the prediction we just found, which would give us a negative residual, meaning it was lighter, 1.65 pounds lighter than we expected. What's the average standard error from the re-expressed model? You can find that by finding the total variation in the weights and then multiplying that by what's left from our coefficient of determination. So basically the 4% of whatever variation we had in the original weights. That's how I did it. But anyway, I think that is given to you in the table at the very bottom. You'll see all the possible re-expressions to the ladder powers. I gave you the correlation, the coefficient of determination, and the standard deviation of the errors of the residuals. Okay, we already went over that. Let's go ahead and do number 16 real quick. Sorry this is going a little long, but if you do need help on number 16, I don't want to leave you out hanging. So let's hanging. It's a pendulum. Oh, that's hilarious. All right, so a student experimenting with a pendulum counted the number of full swings that the pendulum would make or complete in 20 seconds for various lengths of the string. So the shorter length of the string, the quicker the frequency. Okay, so here are her data. So sketches, we want to go ahead and first put the data into the calculator. I think I've already put it in as list 4 and list 5. Yeah, so list 4 is going to be length, number of swings completed is list 5. Notice as the length of the string increases, the number of completed, the period is going to be longer, right? So the number of completed swings is going to be less, right? So it's kind of a physics thing, which is nice. First thing we want to do is actually visualize the data. So we're going to do a scatter plot. Okay, there we go. Then to visualize it, we hit zoom and 9. All right, so do notice here it's kind of it's curving down, so it looks like almost like a reciprocal. So a reciprocal might actually be a good re-expression of this data. So explain why the linear model is not appropriate. Okay, so it's curving down, so it's not appropriate. If we looked at the residual plot would show curvature as well. So I think that's pretty clear. Re-express the data, straighten out the scatter plot, try the reciprocal of the swings. So that's what we're going to do. All right, so back in our calculator, we're going to take the swings, which is our y variable, and take the reciprocal of that value. So go to stat, edit, and for list 6 here, I'm going to go ahead and clear mine out because I've already done it, and I'll show you how to do it. So hit enter to define it, clear out all that stuff. All right, so on list 6, hit enter again. We're going to define list 6 as the reciprocal of list 5. So there's two ways of doing it. You can do a reciprocal as doing like 1 over list 5. So that would work just fine. Another way of doing it, I guess I'll go ahead and do that, and then I'm going to redefine it and clear. So another way of doing it would be list 5 to the negative 1/2 or to the -1 power. That's actually this button. This is a reciprocal button, in case you're curious. And you'll notice these values when I hit enter, they stay exactly the same. So that is the reciprocal. All right, now let's regraph it out. If we wanted to preserve the direction, we actually do the opposite reciprocal. So we need to do negative. So let me do that real quick. All right, clear. So I'm going to do the negative reciprocal. So second 5 to the -1 power. Okay, cool. So that's going to preserve the direction, so it still has a negative association. Not the end of the world if you don't do that, but it is what we like to do in stats. So let's do list 4 to list 6 now with the re-expressed data. So go in here, list 4 to second 6, and then zoom 9. Boom. So it is still negative. Now it's going to be much more linear, much more better. So it should be good. And then I'm going to run a linear regression in order to check it, see how things are looking. So we're going to do list 4 to list 6. I'm going to store the regression equation as y3. So it'll be third option, then hit calculate. And then that's nice, good information. I guess I can actually copy and paste that out there just in case I want to use it for later. And then if I hit graph, it's going to show that line there. If I want to look at the residuals, I can do that real quick just to make sure this was an appropriate re-expression. So second stat residuals and then zoom 9. Okay, cool. Yes, random spread. You could make a case there's still curvature, but that looks like a random spread to me. Okay, so it's not clear curvature. So I think we're done re-expressing the data. All right, we can get our model from here. We can also just plug the values in to get to be able to predict a number of swings in 20 seconds. So length in inches. Okay, yeah, so for the length in inches, how many of them are in there? Okay, yeah, that makes sense. So we re-expressed it, we're good to go. Create an appropriate model, that's what we have here, except it's negative, which is what we actually want, sorry. Estimate number of swings for a 4-inch string. So to do that, all we want to do, second quit, I'm going to go to variables, y variables function, y3. I'm going to evaluate this for 4-inch string. Okay, so then remember that's the negative reciprocal. So to get it back to the original, which would be the number of swings, we want to take the negative of the answer and then the reciprocal. So negative that answer and then the reciprocal, and that should bring it back to a positive 22.8. Okay, so we would expect 22.8 completed. The period would be 22.8 or completed swings. All right, what about 48-inch swing? That's probably, if I had to guess, that's going to be extrapolating. It is, because that's beyond our data set, which is fine. So then take that value, do the negative of the value, and then the reciprocal to re-express it back. So now with a length of 48, we would only expect 8, essentially. Was that actually 48? Yeah. No, because our number of swings was less than that. Yeah, okay, so our highest length was 30. Yeah, so it was extrapolation. Well, how much confidence would you place in these predictions? Well, but I think both 4, we didn't do one shorter than 4, we didn't do one longer than 48. So both of those are extrapolations, so we wouldn't hold much confidence in those values. Okay, that's it. So sorry that was a little bit long. Hope you're able to follow along with it. Another thing is, missed some of you guys in class, so I guess you'll be doing these things online. It's probably a lot easier for me to explain it and for you to ask questions, and I can go back and forth with you. So I'll encourage you guys to come to class. Otherwise, it's kind of like you go a whole nother week without having any interaction. And anyway, so it's kind of sad. But anyway, I'll see you guys soon. Have a good day.